On December 24th, 2024, while most of the planet was busy unwrapping gifts and settling in for holiday films, NASA pulled off something scientists had long insisted was simply not possible. A spacecraft about the size of a family car flew straight into the atmosphere of the Sun. Not toward it, not near it, into it. And it was traveling at 430,000 miles per hour, which makes it the fastest object human beings have ever built. At that velocity, you would cross from New York to Los Angeles in roughly 20 seconds, and the moment it slipped behind the Sun, every signal went dark. The team in Mission Control had no way of knowing whether their machine was still intact. All they could do was wait. This is the story of the day we reached out and touched a star, and of everything that star handed back to us. Most people assume the Sun is deadly for the obvious reason that it is hot. And that is true enough. Its surface burns at around 10,000 degrees Fahrenheit, already a number the human mind struggles to hold. But the surface is not the truly strange part. The truly strange part is the corona. The corona is the Sun's outer atmosphere, a vast invisible shell of plasma that stretches millions of miles outward in every direction. And the corona is not merely hot, it is bizarrely, almost absurdly hot. While the surface sits near 10,000 degrees, the corona climbs to between 1 and 3 million degrees Fahrenheit, as much as 300 times hotter than the layer directly beneath it. Sit with that for a moment, because it breaks the rules we thought governed heat. Step away from a campfire and the air grows cooler the further you go. That is about as basic as physics gets. Yet the Sun does the precise opposite. Move outward from its surface into the corona, and the temperature soars. Physicists named this the coronal heating problem, and for more than 80 years it stood as one of the deepest unsolved riddles in all of astrophysics. But this is not a puzzle for puzzle's sake. From that corona is born the solar wind, a ceaseless torrent of charged particles streaming away from the Sun in all directions at speeds between 200 and 500 kilometers per second. That stream reaches us. It strikes Earth's magnetic field, and when it strikes hard enough, it spawns geomagnetic storms that can disable satellites, scramble global positioning, choke radio links, and overload entire power grids. So studying the Sun is not an idle pursuit. It is about defending the machinery that modern life depends on. Before the mission itself, there is a story worth knowing, because the spacecraft carries a person's name, and that almost never happens. In 1958, a young astrophysicist named Eugene Parker wrote a paper arguing that the Sun continuously throws off a flow of charged particles that travels across the whole solar system. He called it the solar wind. When he sent the work to a leading journal, the editors returned it. The reviewer, a respected scientist, declared it at odds with settled physics and unfit for print. Parker appealed. The paper ran only after the editor-in-chief, Subramanian Chandrasekhar, Subramanian Chandrasekhar, a future Nobel laureate, stepped in. 2 years on, spacecraft confirmed Parker had been right all along. The solar wind was real, exactly as he had described it. Over the decades, Parker became one of the towering figures of solar science. So when NASA prepared to send a probe straight into the Sun's atmosphere, it did something it had never done in its entire history. It named the spacecraft for a living person. Parker was 91 when it launched. He stood on a Florida launch pad and watched his namesake climb into the sky. He died in 2022 at 94, having lived to see his machine rewrite our understanding of the very star he had spent a lifetime studying. That detail tells you how enormous this mission was felt to be, even before it left the ground. Now the engineering problem that robbed designers of sleep for decades. How do you build a craft that can operate inside a star's atmosphere? The sun-facing skin of the Parker Solar Probe reaches around 2,500 degrees Fahrenheit during its closest passes. That is hotter than lava, hot enough to melt steel, aluminum, titanium, and nearly every metal you could name. And yet, the instruments sitting just behind the shield run at about 85 degrees, essentially room temperature, protected by a slab only 4.5 inches thick. The solution is among the most elegant things NASA has ever produced. The shield, formerly the thermal protection system, is 2 panels of carbon-carbon composite wrapped around a core of carbon foam. That foam is 97% air, extraordinarily light, extraordinarily strong, one of the finest thermal insulators ever flown. Its sun-facing side wears a special white coating that bounces most incoming light away rather than soaking it in. Here is the part that startles people. The corona burns at 1,000,000 degrees, yet the spacecraft does not vaporize. Why? Because temperature and heat are not the same thing. Temperature measures how fast individual particles move. Heat measures how much energy those particles actually deliver when they collide with something. The corona is searingly hot, but it is also nearly a perfect vacuum. There are very few particles per cubic centimeter. So while each particle carries enormous energy, there are so few of them that the heat actually dumped onto the shield stays manageable. The probe is not swimming through a 1,000,000-degree bath. It is surviving because a 1,000,000-degree near vacuum is something a well-built carbon shield can take. There was one more challenge almost nobody mentions. At 430,000 miles per hour, the thermal forces clawing at the craft are colossal. Engineers fitted flexible joints so the frame could flex and give rather than stand rigid and shatter. The spacecraft was built to bend so that it would not break. Parker Solar Probe lifted off in August of 2018, but it did not aim straight at the sun. It could not. The geometry of the solar system makes a direct dive almost impossible. A craft leaving Earth carries too much orbital speed and would overshoot into a wider orbit instead of falling inward. So NASA used a gravity assist, borrowing a planet's pull as a slingshot to steer and slow the probe. The planet they chose was Venus. Across 6 years, Parker swung past Venus 7 times. Each pass bled off speed and cinched the orbit tighter around the Sun, like reeling in a line. Each loop set a new closest approach, a new perihelion, per-a-he-li-un, before swinging out and falling back in, nearer than before. And during those 6 years, it was already making discoveries. It found the solar wind near the Sun far more tangled and turbulent than anyone had guessed. It detected strange zigzag reversals in the magnetic field, structures nicknamed switchbacks, far more numerous than predicted, and seemingly key to flinging solar particles to astonishing speeds. It flew through giant coronal mass ejections, those vast plasma explosions, measuring them from the inside for the first time ever. The final Venus flyby came in November of 2024. After that, there was nothing left but to wait for Christmas Eve. On the morning of December 24th, 2024, the team at the Johns Hopkins Applied Physics Laboratory in Maryland was not celebrating. They sat at their consoles watching telemetry and waiting for their spacecraft to vanish. As Parker fell toward its closest pass, it entered a communications blackout, a zone so near the Sun that radiation from the corona drowns any signal the craft can send. They had planned for it. But knowing a thing and living it are not the same. At some point that Christmas Eve, the machine they had spent over a decade building and nursing through 6 tightening orbits went silent. No telemetry, no beacon, nothing. There it was, 3.8 million miles from the Sun's surface, racing at 430,000 miles per hour, flying on autopilot through a star's atmosphere with no way to take a command or send a word. For comparison, Mercury, the nearest planet, never comes within 28 million miles of the surface. Parker was more than 7 times closer than Mercury ever gets. On the evening of December 26th, 2 days after closest approach, the Operations Center received what it had been waiting for: a beacon tone, a simple signal reporting the spacecraft's health. It said, in effect, "I am here, I am working, all is well." The room erupted. Engineers who had given years of their lives wept openly. When the full science data began flowing home in early January of 2025, researchers finally had what they had never possessed: a close view of the corona from the inside. Not from a distant telescope, from within. And the data began answering questions left open for decades. The probe's whisper camera, the wide-field imager for solar probe, caught the solar wind being born, streams of plasma peeling off the corona and organizing into the patterns that eventually reach Earth. Scientists likened it to finally watching a river at its source after a lifetime studying it far downstream. The data also captured something only ever predicted in theory, a phenomenon NASA calls the solar wind U-turn. When the Sun launches a coronal mass ejection, not all the material escapes. Some loops back, drawn in by the Sun's own magnetism, reshaping the corona and steering the next eruption. Parker filmed it directly, understanding that feedback is vital for better space weather forecasts because it helps explain why some storms hit so much harder than others. And then there is the coronal heating mystery. Early data points toward those switchbacks as one of the main ways energy moves from the surface into the corona, heating it to millions of degrees. Not one tidy process, but a tangled mix of magnetic reconnection and turbulent waves, and Parker is finally giving scientists the resolution to map it. 80 years of mystery may be close to an answer. Parker has kept making close passes throughout 2025, each matching its record of 3.8 million miles and 430,000 miles per hour. The Sun is near the peak of its 11-year cycle, so storms are more frequent and fierce, and Parker is gathering data right in the thick of it. But think about why this matters in practical terms. Today, when a major storm approaches, operators get somewhere between 15 minutes and a few hours of warning, barely enough to safe a satellite, let alone shield a power grid. A storm on the scale of the 1859 Carrington event could cascade through grids across whole continents, with recovery measured in months or years, and a price that would dwarf almost any natural disaster on record. The data Parker is collecting at the source is the foundation for genuinely reliable early warning. Instead of 15 minutes, we could one day speak of days. That is not just interesting. It could protect trillions in infrastructure and the millions who rely on it. On December 24, 2024, a machine made by human hands flew into the atmosphere of a star. It endured what would vaporize ordinary matter. It moved faster than anything we have built. And it returned carrying data that is already rewriting the textbooks. For thousands of years, every culture that gazed up treated the Sun as untouchable, a god, a mystery, a thing beyond reach. NASA reached anyway. So here is the question worth leaving in the comments. If we can fly into a star, what should we dare to touch next?